Okay, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good night. Thanks for joining this session. Okay, maybe you can comment in the live chat. Can you see my voice? Can you see my voice clearly? Okay. So thank you for joining. So this session I will continue the previous session, introduction to stiffness method. So before we continue, I would like to revise a little bit about what we have discussed previously. Okay, so we just go through the slide, okay, very quick. Okay, so the learning outcome when we analyze structures using stiffness method. The keyword that everyone should understand is about unconstrained and constrained degree of freedom. Unconstrained and constrained degree of freedom, because before we can analyze either truss or frame or beams, so we have to identify according to unconstrained and constrained degree of freedom. Basically, it is based on support system. Or we can also call it as boundary condition. Okay, so we have to be able to do that. So this is very important, because in unconstrained system, we have unknown displacement. In unconstrained, we have unknown displacement. In constrained system, we have unknown reaction. Okay. And after that, we will actually subdivide the structure into elements. So, and by using formula to calculate element stiffness matrices, okay, we will produce the structure stiffness matrix. So basically, we have to analyze structure, and in order to do that, we have to divide the structure into element. We use the formula given for element stiffness matrix. We calculate element stiffness matrix, and then we combine back to produce the structure stiffness matrix in the global coordinate system. Okay, and we will apply what we call as force displacement properties. It is force displacement equation. Q is equal to KD. We also call it as stiffness equation. And when we apply the stiffness equation, we should be able to solve for the unknown displacement and a reaction at the support. Unknown displacement, reaction at the support. Okay, and for member forces in truss, we have to apply another formula in the stiffness metric method as well. Okay, about the member annual identification, so we have to label all joints in numbers. Okay, we have to label all element also in numbers. We have to label degree of freedom in numbers according to unconstrained and constrained degree of freedom system. We have to put the arrow which is parallel with each element, and the arrow we can put in any direction that we like. Doesn't matter, you can put in any direction. And one more thing is we have to put coordinate. We will use coordinate to identify Cx, Cy, or lambda x, lambda y, because in the formula to calculate element stiffness matrix, we in the formula inside the formula is Cx, Cy, okay, to get the element stiffness matrix. But in the stiffness matrix for element, most important is the degree of freedom label. So we have to be able to label the degree of freedom correctly from near to far end. So from the arrow, we have to be able to identify which is near end node, which is far end node, and after that, each stiffness matrix for element we have to label according to near near condition and near end condition and far end condition, near xy, far xy. Okay, so that is very important. So we will refer to the global coordinate system. So in the formula, we have local coordinate system and global coordinate system. So please refer to the global coordinate system for this course. We just refers to global coordinate system. Okay. And for the difference between local and global, local we have symbol like K prime, and for the global system we just have K, small letter for a small letter of K to represent element stiffness matrix, and capital letter of K to represent the structure stiffness matrix. Okay, so this is about understanding degree of freedom. Degree of freedom is actually based on displacement component. We have three displacement. Basically, in structure, we have three displacement component. We have component in X, component in Y, component in Z. Okay, and in truss, we don't have to count a Z component because there is no moment, there is no rotation. So that is why in truss, we just need to count 2 degree of freedom per node. Okay, so I want to move to, okay, here. Okay, actually I have put this into your notebook. Okay, the textbook chapter number 14. Later on, I will put chapter number 15 and chapter number 16 because in stiffness, in the textbook, truss analysis actually has been discussed under 3 main chapter: chapter 14, chapter 15, and chapter 16. But now we will focus on the truss analysis first. Okay. Okay, let's say since I have actually explained quite detail about node identification, about degree of freedom in previous session. So let's do one example. Now we will focus more on how to establish element stiffness matrices and the structure stiffness matrix. Okay, so let's say we have this. Okay, so this truss, okay, this is 2-member truss. They are node number 1, node number 2, node number 3. Okay, so this has 2-pin support. Okay, we revise back first. 2-pin support. 2-pin support. Distance, this is 3 meter. Okay, and the vertical is 3 meter. The horizontal is 5 meter. 5 meter. Okay, so there are 3 nodes. 3 nodes means we will produce 6 degree of freedom. 3 nodes means we will produce 6 degree of freedom. Okay, because we only count 2 degree of freedom per node in truss, in X and in Y direction. And we need to always follow this direction. Okay, we cannot change the direction to the other way around. Cannot. We have to follow this. Means that later on we will have 6 degree of freedom, 2 at each node. Okay, 2 at each node. However, in labeling the degree of freedom, we have to follow the rules, start from unconstrained followed by constraint system. Okay, there are two elements, element 1, and element 2. Element 1 and element 2. And then we have to put the arrow as well. Okay, the arrow along the member parallel with the element. Okay, with the head of the arrow is always move towards far end. Always move towards far end. So if we focus on element number 1, based on the arrow, 1 will be far, 2 will be near. Okay, for element number 2, based on the arrow, 3 is the far end, 2 is the near end. Okay. Okay, coordinate. We have to label the coordinate as well, because under the formula we have to calculate based on coordinate. So to label coordinate, what we need to do is we will choose one node as origin. So we label as 0, 0. We label as 0, 0, 0, 0. And based on the origin, so we will label the other two coordinate join. Okay, so node number 3, it is 5, 0. And node number 1 is 5, 3. 5, 3. Okay, so now we want to label the degree of freedom. Label degree of freedom. And in order to do that, okay, normally what I will do is I will sketch, okay, according to unconstrained and constraint system. According to unconstrained and constraint system. And after that, I will look at the diagram, and from the diagram, from the support, okay, from the support, there are 4 unknown reaction. From the support, from support, there are four unknown reaction. From support, there are 4 unknown reaction. 4 unknown reaction is Q, unknown is U. From support, from 2-pin support, there are 4 unknown reaction. 4 unknown reaction means that there are 4 here. Okay, 4 DOF will be located under constraint system, the label. Okay, and remaining 2 we will put under unconstrained. Okay, so we identify from unknown reaction. Identify based on the support. Look at the support. Identify how many unknown reaction from the support. So once we identify that there are 4 unknown reaction, so this 4 unknown reaction is actually equivalent to 4 degree of freedom in constraint system. So from that, we just sketch like this, and we have to put 4 DOF at the pin position, the support, at node number 1 and at node number 3. Means we have to put this, okay, 2 at node 1 and 2 at node 3. So this is equivalent to 4 unknown reaction in constraint system. 4 unknown reaction in constraint system, which is equivalent to 4 unknown reaction based on the support, the pin support. Okay, so now we have remaining 2. So remaining 2, we have to put under unconstrained system to complete complete the remaining. Okay, there are 2. Okay, so we have to put another 2 at node number 2 like this. Then only we label. So label 1, 2. Okay, we have to label unconstrained first. When we label, we have to label 1 from unconstrained system. It is advisable not to label 1 from constraint, because from unconstrained there are unknown displacement. Okay, so this is 3, 4, 5, 6. Okay, we must label unconstrained first, because in unconstrained there are unknown displacement. In unconstrained we will have unknown displacement. Okay, means that there are 2 unknown displacement, D1 and D2. 1 and 2 representing D1 and D2, and D1, D2 are the unknown displacement. Okay, and unknown in constraint there are unknown reaction. The symbol is Q. Unknown reaction, the symbol is Q. There are 4 degrees of freedom. Means we will have Q3, Q4, Q5, Q6. Okay, under constraint system. Okay, so all these are the unknown, means this is the output that we will calculate. So we have to calculate D1 and D2. And after that, we have to calculate Q3, Q4, Q5, Q6. Okay. So when we combine back, we will get, when we combine back, we get, so each node has 2 degrees of freedom. Okay, the label we just need to follow. Okay, what we have labeled previously, like this, 1, 2, 3, 4, 5, 6. So here is node number 1, node number 2, node number 3. Okay, so actually this 6 degree of freedom, okay, this degree of freedom, as I mentioned previously in the last session, degree of freedom, we have to look at this in terms of Q and in terms of D. What is Q? What is D? Okay, Q and D, the relationship is Q is equal to KD. That is the relationship. This relationship is called as stiffness equation. This is stiffness equation. Okay, this is stiffness equation. And in stiffness method, all will be written in matrix form. It means that Q will be written in matrix, K also in matrix, D also in matrix. And Q as well as D in stiffness matrix method is called as, this Q is called as nodal forces. And D is called as nodal displacement. Nodal forces and nodal displacement. Okay, we will put the word nodal, come from the word nodes. It means that all Q and D that we analyze in stiffness method, we only calculate the value at nodes. We only calculate displacement at node. We calculate reaction at node. Okay, we do not calculate mid-span displacement, no. Okay, we only calculate the forces and the displacement at nodes. Okay, so what does it mean? If this truss has 6 degrees of freedom, this truss has 6 degrees of freedom, it means that we will have Q 6 value of Q. 6 value of Q. We have D, which is 6 value of D. Okay, and we have K, the structure stiffness metric. The structure stiffness metric K, okay, is 6 by 6 matrix. Okay, so number of this will be based, the size of the matrix will be based on the degree of freedom in the truss. Okay, it will be depend on the number of nodes. So Q, there are 6 value. Okay, at position 1, 2, 3, 4, 5, 6. Okay, so we have Q1 until Q6. It means that we have Q1 until Q6. D, nodal displacement. Nodal displacement, we have D1 until D6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we have K, 6 by 6. 6 by 3, 6 by 6 we label as 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So, in stiffness method, we have to fill in this. Okay, we have to fill in Q, D, as well as K. And after we have all this, then only we can solve for the unknown displacement and also unknown reaction. Okay, so based on this condition, D1 and D2, so this is the concept. Please try to understand. This is the concept. Okay, look at this. Okay, D1 and D2 means this is unknown displacement. And unknown displacement is du. This is unknown displacement. So in the matrix for D, position 1 and position 2, D1 and D2, these two are the unknown displacement. So we have to remain as symbol first. So this is D1, this is D2. Okay, means that we will solve for D1 and D2. This D1 and D2. Okay, and then for Q, if we refer back to this, okay, so in constraint system, there are 4 unknown reactions. In constraint system, there are 4 unknown reactions. Start from 3, 4, 5, 6. All these 4 are the unknowns. So we remain unknown as symbol. So at position 3, this is Q3, Q4, Q5, Q6. Okay, and then okay, we have to put the value for Q1 and Q2, and we have to put the value also for D1 until D6. Okay, so in order to do that, we have to understand the physical meaning of Q and D. Physical meaning of Q and D. Okay, so look at back to this. Okay, so let's say let's say, so this truss has loading 1000 1000 kilonewton, for example. Okay, 1000 kilonewton at node 2. Okay, 1000 kilonewton at node 2. So from this diagram and from the degree of freedom that we label, we have to read the information, okay, in the main diagram. For example, okay, we have to understand the definition, the Q and the D definition. For example, okay, one means in terms of Q, one is horizontal force. One is horizontal force, two is vertical force. In terms of Q. In terms of Q, one is horizontal force, two is vertical force. So we have to replace with value in the matrix. Okay, so compare with this. One is horizontal force at node 1. One is horizontal force at node 1. So look at the diagram. At node number 2, is there a horizontal force? No, there is no horizontal force. Means that the Q1, the value is 0. Q is force, 1 in horizontal direction. So looking at node number 2, there is no horizontal force at node number 2. From the main diagram, there is no horizontal force at node number 2. So Q1 is equal to 0. So we have to put 0 right here. Okay. And then what is Q2? Q2. Q2, look at to the degree of freedom at node number 2. At node number 2. Okay, DOF2 means in terms of Q, it is vertical, in vertical direction, force in vertical direction. Force in vertical direction. Is there a vertical force at node number 2 given in the question? Is there any vertical force that is subjected at node number 2 in the question? So look at the question. Okay, so at node number 2, there is a vertical force 1000 kilonewton. 1000 kilonewton. Okay, at node number 2 in vertical direction. At node number 2 in vertical direction. What does it mean? What is the value of Q2? What is the value of Q2? Can you write something in the live chat? What is Q2? What is Q2? Okay. Again, we have to replace the Q1 until Q6 with value. Okay, we have to replace with value. Anyway, we have to remain unknown as unknown. We have to remain unknown as unknown, and remaining we have to put value. Okay, so that is why importance of understanding the meaning. What is Q1? What is Q2? Anyway, it is depending on how we label the diagram. Depending on us. Okay, so at node number 2, there is a vertical force downward 1000 kilonewton. 1000 kilonewton. And based on the degree of freedom at node number 2, vertical direction, it is 2. Means that Q2, it is Q2. Q2, since it is opposite this direction opposite with 1000 kilonewton. So once it is opposite, so it is negative. So Q2 is negative 1000. Q2 is negative 1000. If the direction is in same direction, so it is positive. If it is in opposite direction, it is negative. Okay, so the answer is correct. It is negative 1000 for Q2. So this is negative 1000. So everyone should be able to fill in this like this. Okay, so there are 6 value of Q, because there are 6 degree of freedom. So we have Q1 until Q6. Okay, unknown remain as symbol. Unknown remain as symbol. So there are 4 unknown reaction. There are 4 unknown reactions start from Q3, Q4, Q5, Q6. So there is a boundary here. This is the boundary between unconstrained and constrained. Okay, so if under constraint, if in constraint system, there are unknown. So in constraint, it must be in opposite condition. Means unknown versus known. Unknown versus known. Q3 until Q6, all these are unknown versus known. So the upper part must be known value. We must put the value. We cannot put symbol. Okay, we must put value. It is always in opposite condition. 0 and negative 1000, then Q3, Q4, Q5, Q6. Okay, so let's do the same for D. Let's do the same for D. D1 and D2, this is the boundary between unconstrained and constrained. The boundary. And between unconstrained and constrained, the condition is always opposite. Opposite means if one part is if one is if unconstrained is unknown, constraint must be known value. The condition must be opposite. D1, D2, now D1, D2 are unknown. So D3, D4, D5, D6, we must put value, because unknown versus known. Unknown versus known. Okay, previously under Q, it is known versus unknown, between unknown, unconstrained and constrained. So what are the value for D3, D4, D5, D6? D3, D4, D5, D6. Who knows the value? D3 sini ya. D3, D4, D5, D6. What does in terms of D? In terms of D, in terms of displacement, D3 means horizontal displacement. 4 means vertical displacement. 5 horizontal displacement. 6 vertical displacement. So what are the value? So remember, not 1 and not 3, okay, is actually the support. There are 2 pin support at node 1 and node 3. So means that when it has support, there is no displacement. It cannot move. So D3, D4, D5, D6 equal to 0 because of the support. There is no displacement at support. There is no displacement at support. So all value are 0. Okay, so we have to put this. So this is 0, 0, 0, 0. Okay, so only if you can label like this, then only you can proceed to the next stage. Okay, if you cannot label this, if you cannot fill in this correctly, you cannot solve for the unknown displacement and unknown reaction. Okay, you have to be able to label all this. Okay. Okay, clear about this, yeah? Okay, we will use the stiffness equation, to solve for the unknown displacement. Unknown displacement is the first output, like I have mentioned in my previous session. Remember, stiffness method is also known as displacement method. Why it is called as displacement method? Because displacement is the first output. Displacement is the first output. So we have to solve displacement first, then only we can solve for the unknown reaction. Okay, so in order to do that, we have to be able to label Q and D in matrix form. Okay, like this. Okay, now we want to focus on K. Capital K represents structure stiffness matrix. Okay, it is 6 by 6 matrix because of degree of freedom. There are 3 nodes equal to 6 degree of freedom. So now we will establish this K value. Okay, so in order to do that, okay, from this, okay, we will extract one by one element. We will produce K1 for element 1, K2 for element 2 separately, then only we combine. Okay, now I want to extract element 1. Element 1. Okay, element 1. This is element 1. Okay, node number arrow is like this. Arrow is like this. So when this is the arrow, okay, so this will be the far end. This is the near end. Okay, the coordinate is 0, 0 and 5, 3. The coordinate. Okay, the degree of freedom, 2 at each node. This is 1 and 2, 5 and 6. 1, 2, 5, 6. We have to refer back to this. 1, 2, 5, 6. 1, 2, 5, 6. Okay. Okay, this is element number 1. Element number 1. L for this element equal to the length. Length for this element equal to 5.83. 5.83 meter. Okay, this is the length. Okay, let's find the formula to calculate this. The formula. Okay, let me show you the appendix. I will take from the previous semester. Okay, I will put appendix here. Okay. Okay, temporary. Okay, later on I will put under the content library. Okay. Okay, this is appendix. This is appendix given in the final exam. Okay, appendix for truss structure. So the latest last 2 or 3 semester in final exam, we just change Cx Cy to lambda x lambda y. Doesn't matter, both can be accepted. Okay, so this is what I mean about the local system where the symbol is k prime. So you don't have to refer to this and this. Okay, straight away for the structure, for the element stiffness matrix, please refer to this formula. Okay, this is the formula to calculate element stiffness matrix. It is 4 by 4. It is 4 by 4 because element consists of 2 nodes, and 2 nodes total, we have 4 degree of freedom. Okay, we have 4 degree of freedom. And most important, this is 4 by 4 matrix. 4 by 4 matrix. And this is actually based on the near and far end position. So the first two, it is actually the first two is for near, and the last two is for far. So when we label, we have to label near first, then followed by far. Okay, and under near nodes, we have x and y. Under far end node, we have x and y. So that is why the label is near y, far y. Near x, near y, far x, far y. Same goes to the vertical side. Okay. Okay, what is inside the formula? Okay. Actually, the value is quite simple. This is cx square, cx cy. Okay, the matrix should be symmetry. So this is negative cx square, negative cx cy, and this equal to this because it is matrix, and matrix is must be symmetry. Okay. And one thing is, this value is actually same to this, and this value also same but just negative value. Okay, so okay, the pink okay, the pink the highlight pink ni, okay, dua-dua ni equal. Okay, the blue, this two is also equal. Okay, means that we just need to focus on how to get cx and cy correctly. Cx and cy correctly, or lambda x or lambda y correctly. Okay. Okay. Okay, back to this. This is element number 1. The length of this element we have to calculate using trigonometry. Okay, the length is 5.83. Okay, in the element, we have labeled the near and far nodes. This is very important. Okay, we have to label the near and far node correctly. Okay, it will be based on the arrow. Okay, the degree of freedom, we just need to put the label that we have just defined under the previous step. 1, 2 at node number 2 near node, and node number 1 for end node is 5, 6. Okay, and the coordinate. Okay, now we want to calculate cx and cy, or lambda x and lambda y. Okay, to calculate Cx, okay, I normally choose to write Cx and Cy. Okay, to calculate Cx, look at the x coordinate. To calculate y, look at the y coordinate. That's all. Okay, to calculate Cx, look at the x coordinate 5 and 0. Okay, it is 5 minus 0 divided by L. Divided by L, L is 5.83. Okay, it is far minus near. Far minus near. The far value is 5. The near value is 0. It is far minus near divided by L. So we get 5.83. It is 5.83 divided by, it is 5 divided by 5.83. So it is 0. It is 0.858. 0.858 for Cx. And for Cy, we have to look at the y value. It is far minus near. Y value, look at y value. Far minus near. Far, 3. Near, 0. Divide by L, 5.83. So we get 3 divided by 5.83. 3 divided by 5.83. So this is equal to 0.515. Okay, then we have to put into the formula. This formula, we have to put into this formula. And we remain, normally K, we will write in terms of AE. So we remain AE outside the bracket. Okay, we will write the equation, the K in terms of AE. Okay, so this is the formula. So we substitute. Okay, wait. Okay. Okay, we will calculate K1. K1 now. Okay, the formula is AE over L. AE over L. Then we have to calculate with CX, CY, just like in the bracket. Okay, the label. Okay, the label will be follow. The label will be follow this. 1, 2, 5, 6. 1, 2, 5, 6. Remember, this is for near, far, x, y, x, y. Means that this is 1, 2, 5, 6. 1, 2, 5, 6. Okay, so for K1, it is K1, the length is 5.83. 5.83. Cx square. Cx squared is 0.858 square equal to 0.736. Please check. 0.736. Cx cy is 0.858 times 0.515. Okay, please check together. 442, 442. This one is 0.442 Cx cy. Then negative 0.736 442 and negative 0.442. Okay, the metric is symmetry. This is also 442. This is negative 736 and 442. Then this value cy squared. Cy squared, we refer to cy. Cy is 0.515. 0.515 square. So it is 265. 265. So this value is 265. 265. Okay, 442 and 265. 265. Okay, symmetry means this is also 442, 265. 265. Okay. And then 736, 442. This is 442 and 265. 265. Okay. So this is K1, but this is not finished yet. This is not finished yet. So we have to divide by 5.83. We just need to remain AE outside the bracket. Okay. So AE 736. 0.736 divided by 5.83, we get 0.126. 126. 0.442 divided by 5.83 is 0.076. 0.76. This is 0.776. Okay, 0.76 and 0.265 divided by 5.83 is 0.045. 0.045. Okay, 126. 0.76. 0.76 and 0.45. Okay, 126. 126. 0.76. 0.76. 076, 076, and 045. 126, 076, 076, and 045. 045. Okay. So this is K1. This is K1. This is K1 in terms of AE. But remember, we have to label the degree of freedom. Label the degree of freedom. Label start from near. Okay. So that is why important of having this diagram. Okay. So we will label as 1, 2, 5, 6. 1, 2, 5, 6. So this is 1, 2, 5, 6. 1, 2, 5, 6. Okay, this is K1. Stiffness metric for element 1. K1. Okay, move to K2. Move to element number 2. For element number 2, L is 5 meter. L is 5 meter. Okay, arrow like this means that this will be the far end. This is the near end. Okay, the coordinate 0, 0 and 5, 0. 5, 0. Okay, the degree of freedom, based on the arrow, it is 1, 2, 3, 4. 1, 2, 3, 4. Okay, 1, 2, 3, 4. So we have to calculate Cx and Cy. Cx, Cy. Cx, look at the x coordinate. Cy, look at the y coordinate. Okay, so it is far minus near. For Cx, far is 5. Near is 0. Divide by 5. Divide by 5. So it is 1. It is 1. And for Cy, it is 0 minus 0 divided by 5. This is 0. Okay? So from this Cx and Cy, we have to produce K2. And the label is 1, 2, 3, 4. 1, 2, 3, 4. So, I copy this. No. I want to take only this. Okay. So, for K2, okay, this is K2. K2, Cx square. The first value is Cx square. Cx square. Cx square means 1 square. 1 square. And we have to divide by L. Original L here, right? So we have to divide by L. So 1 divide by L. L is 5. It is 0.2. It is 0.2. 1 divided by 0.5. 1 divided by 5. It is 1 over 5, 0.2. So this is 0.2. Okay, this is 0.2. Okay, the second value here, okay, it is Cx, Cy. Cx, Cy 0. So this will be 0. 0, and then negative 0.2, then 0, 0. Okay. Okay. This value is cy squared. Cy squared means 0. So this is 0. This is also 0. This is also 0. Okay, this is for K2. 0, 0, 0.2, 0, just like this. Okay. Okay. So the label we have to follow this 1, 2, 3, 4 because we follow the arrow. And we have to label outside the bracket. 1, 2, 3, 4. 1, 2, 3, 4. So this is the stiffness matrix for element number 2. For element number 2. So now we have K1 and K2. Okay. And to produce the structure stiffness matrix, the structure stiffness matrix K capital is equal to K1 plus K2. Okay, even though K1 and K2, the matrix size is 4 by 4. However, the capital K, the structure stiffness matrix, the matrix must follow the number of degree of freedom. Since this has 6 degree of freedom, so we will produce K 6 by 6 matrix. And degree of freedom, which we label in K1 and K2, actually represent the position in the structure stiffness matrix. Okay, so we will produce K from 1, 1 until 6, 6. K from 1, 1 until 6, 6. Okay. Okay, let's do it together. Okay. So, where is it? Okay, we will replace this with the right answer based on K1 and K2. Okay, this is K2. Remember the degree of freedom that we label in the element stiffness matrices. Okay, K2 we have 1, 2, 3, 4, and K1 we have 1, 2, 5, 6. So this 1, 2, 3, 4, 5, 6 representing the position in the structure stiffness matrix. Okay, so I want to copy this. Okay, and put here. Okay, so we have K1 and K2. K1, 1, 2, 5, 6. 1, 2, 5, 6. Okay. Okay. K capital or structure stiffness matrix we must write in order, means from 1 to 6. 1, 2, 3, 4, 5, 6. We must write the value in order. In order. Okay, so this position is 1, 1. This is just a simple matrix like what you have learned previously. This is 6, 6. This is 2, 4, 4, 2. Same value. Okay, just like that. So we have to replace all this with value we get from K1 and K2. Remember, the label, the degree of freedom that we label in the element stiffness matrices is actually the position in the structure stiffness matrix. In the structure stiffness matrix. Okay, so now we want to find the value at position 1, 1. We want to find the value at position 1, 1. 1, 1 means this is 1, 1 plus this 1, 1. 1, 1. Okay, it is 0.2 plus 0.126. 0.2 plus 0.126, same position, 1, 1. So it is 0.326. 326. Okay. Okay, next value is position 1, 2. Position 1, 2, this is 1, 2. This is also 1, 2. Okay, we have 0.076 and 0. So 1, 2 at position 1, 2, at position 1, 2, it is 0.076. 0.076, 1, 2. Okay, next value is 1, 3. 1, 3. 1, 3. So find 1, 3. Find 1, 3 in K1 and K2. Find 1, 3 in K1 and K2. 1, 3 in K2. Okay, we can find 1, 3 in K2, but we do not find K3 in K1. Means that the value is only based on K2. 1, 3 is negative 0.2. Just a simple mathematics. Negative 0.2. 1, 4. 1, 4 is 0. This is 1, 4. 1, 4 is 0. 1, 4 is 0. 1, 5. 1, 5 we get from K1. This is 1, 5. And this is 1, 6. 1, 5 and 1, 6. 1, 5 is negative 0, negative 0.126, and 1, 6 is negative 0.076. Negative 0.076. Okay? And actually, we don't have to write in full. We don't need to write in full because it is symmetry matrix. This value equal to this value. So we don't need to rewrite in full. Just write like this. Okay, so move to the next value at position 2, 2. At position 2, 2. At position 2, 2. Okay, look at K1 and K2 again. Okay, 2, 2. So 2, 2, 0, 2, 2, 0.045. 0.045. 0.45. Okay, next is position 2, 3. 2, 3. Okay, 2, 3 is 0. 2, 3 in K2 is 0. And there is no 2, 3 in K1. Okay, 2, 3, 0. So we put 0 here. 2, 3 is 0. Okay. Next is position 2, 4. Next is position 2, 4. 2, 4 is also 0. 2, 4 is also 0. This is 2, 2. This is 2, 3. 2, 3, 0. 2, 2, 3 is 0. This is 0. 2, 2. 2, 2 is 0.45. 2, 3 is 0. 2, 4 is also 0. 2, 2, 4, 0. Okay. 2, 5. 2, 5. This is the value. Negative 0.076. 2, 5. Negative 0.076. Okay, negative 0.076. 26. 26 is negative 0.045. 26. 26 is negative 0.0045. Okay, negative 0.045. And again, this equivalent to this. Okay, so we don't have to write in full. Okay, next move to 3, 3 value. 3, 3, 3, 3, we get 0.2 only. 0.2. So this should be 0.2. This should be 0.33. 3, 4. 3, 4 is 0. 3, 4, 0. So 3, 4 here is 0. 3, 5 and 3, 6. We don't find 3, 5 in K1. We don't find 3, 5 in K2. There is no 3, 5 in K1 and K2. There is no 3, 5 in K1 and K2. Means we just need to put 0. Okay, 3, 5, 3, 6. There is no 3, 5. There is no 3, 6. Okay, means the value of 3, 5 and 3, 6, we put 0. Okay, next, we move to 4, 4. 4, 4 is 0. 4, 4 is 0. Okay, 4, 4 is 0. 4, 5. There is no 4, 5. There is no 4, 6. There is no 4, 5. There is no 4, 6 in K1 and K2. So we put 0. Okay, next is 5, 5. 5, 5, 0.126. 0.126. 5, 5. 0.126. 5, 6. 5, 6 is 0.076. 5, 6. And 6, 6 is 0.045. 0.045. Okay, so this is the structure stiffness matrix. This is the structure stiffness matrix. So this matrix must be written in order, means from 1 to 6. So this is 1, 2, 3, 4, 5, 6. Okay, so this is the structure stiffness matrix. The structure stiffness matrix. Okay. Okay, so once we get this, we can write the stiffness equation. We can write the stiffness equation. Q is equal to KD. Q is equal to KD. We have established Q and D at the beginning, and we have just produced K, so we combine to have what we call as structure stiffness matrix. Q is equal to KD. Okay, Q is equal to KD. So this is K. This is K. Q. Q, K, and D. Okay, so negative 1000. Okay, so this is what we call as stiffness equation. Stiffness equation or force displacement equation. Okay, stiffness equation, Q is equal to KD. Q is equal to KD. Q is nodal forces. D is nodal displacement. So we have 6 value of Q and 6 value of D. So in Q, there are 4 unknown reaction. Start from Q3 until Q6. Q1 and Q2, we have to put the value. So the value is 0 and negative 1000 based on the loading given in the question. D1 and D2 are the two unknown displacement located in unconstrained system, node number 2. And D3 until D4, the value is 0. The value is 0 because it occurs at the support. At support, there is no displacement. At support, there is no displacement. So this is actually what we call as stiffness equation. Stiffness equation. And by solving this equation, by solving the stiffness equation, we can solve for the unknown displacement. And after that, we will use D1 and D2 to calculate Q3, Q4, Q5, Q6. Of course, we cannot calculate Q first, because we will calculate Q value with D value. Means we have to calculate D first, and once we have calculated D1 and D2, we use this D1 and D2 to calculate Q value. So that is why we have always calculate D1 and D2 as the first output in stiffness method. Okay? Is it okay? So before we end session, I want to, this one actually the website. Later on, I will give you the link. The link. Wait. Okay. So this is example question, Truss question. Example Truss question. Normally, the question will be the same every time, Okay, we start with establish the element stiffness matrix, element stiffness matrices, K1 and K2 and K3 and K4 and so on. Okay, then we combine to get the structure stiffness matrix, and then we will write the stiffness equation. Okay, the stiffness equation is a compulsory step because we will solve for the unknown displacement, we will solve for the unknown reaction using the stiffness equation. We will solve the unknown using stiffness equation. Even though in the question there is no statement asking for writing the stiffness equation, still we have to write the stiffness equation in order to solve for the unknown displacement and unknown reaction. Okay, so this truss basically 1 2 3 1 2 1 1 2 3 three nodes also, two element arrow is given, the DOF is also given. Anyway, the unconstrained is located at node number 3. That is why label 1 2 is in node number 3. Okay. Okay, in summary, there are 6 degrees of freedom because there are 3 nodes. 6 degrees of freedom because there are 3 nodes. Okay, so by looking at the support, there are 2 pin support, means there are 4 unknown reaction. So 4 unknown reaction means remaining is 2. 2 is unknown displacement. 2 unknown displacement, 4 unknown reaction. Okay. So we have to label the coordinate. The coordinate is very important because without coordinate, we cannot calculate Cx and Cy. So we calculate Cx and Cy based on the coordinate. So the formula, as I explained just now, it is far minus near. Look at coordinate x for Cx, look at coordinate y for Cy. It is far minus near divided by L. So once we get Cx and Cy, we just need to substitute into the K formula, the element stiffness matrix. Okay, the K formula, and we will produce K1 and K2. But what most important is how we label the degree of freedom for element stiffness matrix. Okay, for K1 by looking at the diagram for element number 1 here, element number 1 based on the arrow, the label should be 3412. The label should be 3412 because we label based on the arrow. Because the arrow will guide us which is near and not, which is far and not. And when we label element stiffness matrix, we must label start from near to far. So we must label K1 as 3412. Okay, this is very important. Okay, and for element number 2, based on the arrow, so near is 3, near is not 3, far is not 2, so we will label DOF as 1256. So K1 here, so the value is the label is 3412. We must label like this. And for K2, the label, okay, is 1256. Near, too far. Then we have to repeat the same process like what I have just shown to you. Okay, we have to combine K1 and K2 to have the structure stiffness matrix. To have the structure stiffness matrix, we have K is equivalent to K1 plus K2. Okay, remember the label, the DOF that we label in element stiffness matrices is actually the position based on the 6 by 6 position in the structure stiffness matrix. And structure stiffness matrix, capital K for the structure, must be written in order 1 to 6. So we have to find the value, position 1, 1. We have to find 1. Where is 1, 1? 0.080 here. 1, 1 is 0.080. Okay, 1, 1 plus with 0.038. So we get 0.118. So we do the same until we get the whole value. 66. So we find 66. 0.117. Okay, do one by one step like just now. Okay, so we get 6 by 6 matrix for the structure stiffness matrix. And okay, we have to define nodal forces and nodal displacement. Nodal forces and nodal displacement. Okay, the Q1 and Q2 we must put value. We must put value because it is known versus unknown. Okay, for Q it is known versus unknown. Okay, for D1 and D2, D1 and D2 unknown, unknown versus known. That is why 3, 4, 5, 6 we 3, 4, 5, 6 we put value, known versus unknown. So after we have defined Q and D in matrix, and we have also established K, structure stiffness matrix. So when we combine, we produce the stiffness equation. When we combine, we produce stiffness equation. Okay, so the line after position 2 is the boundary. We separate between unconstrained and constrained. We separate between unconstrained and constrained. And actually, when we want to solve for the unknown displacement, we just consider okay, the unconstrained system only. So means that if the unknown displacement are 2, means that we will solve uh, the unknown displacement by solving 2 simultaneous equation. So finally we get in matrix form, just like what we have done in flexibility method. When we have 2 redundant, we have equation that we have written in matrix form like this. Okay, but now the unknown is displacement. The unknown is displacement. So this matrix is actually equivalent to 2 simultaneous equation which we can solve easily using calculator. So we get D1 and D2. We get D1 and D2. Then after we get D1 and D2, we will substitute. We will substitute into the stiffness equation again. So this D1 and D2, this D1 and D2, to calculate the unknown reaction, we have to substitute back into the equation, into this stiffness equation. So we have to, and after that we have to use the matrix knowledge that you have learned previously about the multiplication, matrix multiplication. We will get Q3 until Q6. Okay, so this is actually the process in the stiffness method. Okay, so we solve the unknown reaction. We solve the unknown reaction using the unknown displacement. Okay, the unknown displacement. And finally, for the truss, we have to continue to calculate member forces. So member forces, we have to apply for this formula to calculate the member forces. So since there are two members, so we have Q1 and Q2, and since the member forces is element. The member forces means Q for element. Q for element. That is why kat sini kita again use the small letter. So in stiffness method basically small letter represent element, capital letter represent structure. So when we go to this step, member forces, we will use Q, a small letter of Q to represent the member forces. Okay, to represent the member forces. Okay, so we have Q1 and Q1 and Q2 lah. Q1 and Q2. Okay, the final one is Q1 and Q2. So actually this one, this slide I have convert into website. Okay, and I will put the link for this in Teams. Okay, in Teams channel. Okay, so I think that's all for this for today's session. So thank you for joining. I hope you understand all about truss analysis using stiffness method. So this is the basic lah, the basic question about trust without considering temperature changes, without considering fabrication error, and without considering support settlement. And of course, when the effect, this effect, temperature changes, fabrication error, support settlement is given in the question, we have to consider that. Okay. So I hope you understand all about this. Inshallah, we will continue our lesson to cover example temperature changes example, fabrication error example, and as well as support settlement. Actually, all example are given in the textbook, and I am preparing also the module 2 step by step, and hopefully after this we can use the module, especially for week, not next week. Next week class physical inshallah will be held as usual. But for the following week, we have to replace all with online classes, night classes, because the whole week, everyone in the faculty in school will be busy with the big program event, the big event in Dewan Besar UiTM. Okay, so that's all for this session. If you have question, please ask. Okay, you can come to my office to ask question. Okay, thank you very much. Thank you for joining. Okay, we will meet again in the next session. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.